I will just let everyone join. So we will wait a few minutes. Okay, so hi and welcome to Danish Sound Cluster's webinar. Today's subject is data simulation for AI. And we are very fortunate to have with us today 3 speakers who will introduce us to their research and their work on the topic. First of all, we have Rasmus Kongsgaard Olsen from GN Audio, and he works in the research department for AI. He will talk about simulating audio data for AI training and Jabra's research around the topic. Then we also have Romain Cyricel, who's an associate professor at Université de Lorraine, and he will talk about sound event detection with synthetic soundscapes. Then we have Toon van Waterspoel, associate professor at KU Leuven, and he is also head of Stadia Center. He will talk about simulation of room acoustics. And then a few practical things from Danish Sound Cluster. Do remember to ask questions. We have the speakers here for the same reason. And when you ask questions, please put it in the Q&A chat function in the bottom of the Zoom window, because that will help us answer them in the right order and structure a bit more. Then we also have a chat function. And that is more if you have like relevant links or you want to add a comment or something like that. Then I have to inform you that we are recording the webinar and that the recordings and the presentations will be sent to you afterwards. And then we also have in the end a questionnaire popping up. And that questionnaire will help us be more relevant in the future and improve our webinars. So please spend 1 minute answering that. So that was all for me, and I will then hand over to Rasmus.
Hello, everyone. I hope that you can hear me. Just need to do like this. Okay, and now I can see it. I'm happy to represent GN and Jabra today. Thanks to Stine, Shelley, and Danish Sound Cluster for making this happen. Today, I'm basically going to talk about using simulation of audio as an alternative to using recorded databases of audio to train AI audio processes. And this from a Jabra research perspective, so a slice of what is going on now. First, I'm going to say just a few words about GN and myself. Don't worry, it's not going to turn into a lengthy company presentation. On one side, GN is a developer of hearing aids through brands such as ReSound, Beltone, and more. On the other side, in GN Audio / Jabra, that's where I'm employed. We make and market communication equipment. That is mainly headsets and speakerphones. It's very nice products like this one that you can use to call your mom or participate in a professional meeting or do a webinar and so on. Lately, the SteelSeries portfolio of gaming products have been added to the GN family. My personal role in GN is to work as a scientist in the research and innovation department of GN Audio. And our primary role in the company is to explore new technologies. When we find something promising and useful, we join forces with the rest of the R&D and try and develop and mature it and carry it to products. It could, for example, be new algorithms for embedded audio processing with AI inside. This step to mature and make end users happy in our products is really a big task. And that's also a point I'll try to stress a little bit when creating the data. With that being said, I'm ready to start slowly introducing the topic of today, namely simulated audio. If we look a little bit at the quite large range of products that we do, I think it's easy to imagine that simulating audio will not be a one-size-fits-all. We have, for example, consumers running around in train stations, parks, windy conditions with microphones situated far away from the mouth. We have users sitting in very noisy call centers, a lot of talking colleagues around them. And we have people who are relying on augmented hearing to get some help in challenging conditions and so on. And for each of these audio/acoustic tasks, we could think of doing different AI processes that are trained on real or simulated data. But anyway, we would need to understand very closely the acoustics and the use cases involved in order to get the data right. And if we do not get the data right, then the product will not perform as you would expect in the end, and we'll have not so happy customers. So let me start with an example of one use case. So this is one of our very nice speakerphones, a Speak 750, and in a conference call, the microphone is picking up a mixture of voices from users in the room, noise from noise sources, and acoustically fed back echo from the loudspeaker. The speakerphone's loudspeaker is playing back the incoming voice from the far end of the conversation so that the user can listen to it. And it needs to be removed so that the guy in the far end does not hear his own voice delayed, because that's very disturbing. So just to illustrate this, I'll play this sound clip back, if I can do that. Yeah, and let's listen to it.
That's good. You're going on
Thanks a lot.
vacation?
Thanks a lot. Yes, I would be very soon in vacation, and I'm really
So
looking forward for that.
Where are you going?
You know, I already told you that I'm going to France and in
Speak
Paris.
speaking.
But
Sorry?
there are many places in France, really. So is
Yeah,
it,
that's true. You're right. I'm going to Paris.
to
So
Paris?
yeah.
So the French guy we heard speaking here, going to Paris, that's actually the signal we need to remove so that we can hear the other ones. It's by far the loudest presentation. As an example, at the end of this presentation, I will show how we simulated data for this problem, and we trained an AI system to remove the echo, and you can listen to that as well. So just a few words on where data fits into the DNN training pipeline. Here we have an example of a pipeline for training an AI echo control. And I'll not go through it all, but what is sort of key of today's talk is that we have data from which we can form a dirty input, maybe consisting of speech, echo, and noise in this example. And we have a target speech, and we want our neural network to perform a mapping from dirty speech to clean speech, and we specify how this, what kind of qualities we like in the clean signal through the loss function. That's not the talk of today, but we need to get the data for the DNA pipeline, and as I was hinting earlier, we need to understand our use cases very well. So in a classical DSP solution, no AI inside, what we want to achieve in the end is a product that makes the end user very happy in all cases. And that means that the DSP code needs to do a lot of branching and if then else to work in all cases. We cannot have sort of any problems in the products. And to do all this right, you need to understand the problem and domain very in great detail, actually. But same is actually the case, I would argue, for if you do it with AI. You need to understand the problem very well so that you can get the data exactly right to match reality, but also so that you can specify a loss that's relevant and DNN architecture that will perform your mapping. But these two are not the focus of today. But in the end, the goal is to get a very nice quality, and you need to know the domain in great detail. So training on real data is often not feasible. I write here, why not? Well, imagine that you are inviting 200 people to go to each of 100 rooms to speak, each person in 10 different positions in each room, and you have 25 different background noises that you also want to sample. This is simply going to take a very long time, a year or something. And then the marketing or the management tells you, now we need another product with microphones in a slightly different position or different use cases, and you can start all over. And that is sort of the cue for let's simulate the data. So it can be a lot faster and cheaper. It's flexible to moving the microphones or the sound sources around. And it is also sort of, this is also a key, I think, key advantage, that it allows for development and debugging. If you have problems with your data or you want to add use cases or change something slightly, then you can do it by changing the simulation machine. It takes a lot of different aspects to get your audio simulation right. Because in the end, we need the training data to match reality or the test data. We don't want to fit to training data and not generalize to reality and have poor performance in reality. That's what we want to avoid. So let me just give you one example of, let's call it compromised data. A machine learning method was very good at classifying images, especially images of horses versus other categories. But as someone in the literature found out, that was because all horse images had small copyright tags at the bottom. And that was really what the neural network learned. It found out that, if there's a copyright tag in the bottom, it's a horse. So they made a small experiment. Let's put tags on other images, race cars, for example, then they also became horses. Something like this, in our experience, can also very easily happen for sound. So we want to avoid these giveaways, fingerprints, artifacts in training data that will confuse our learning and generalization. So let me just very briefly go over some of the basics of acoustics. I'm happy that I have Tone and Romain following here to dive more into this. But the basics of room acoustics, that it is linear and that you can simulate sound sources in a room by convolution. So you can take a clean source and you can apply the impulse response through convolution, and you will get a representation of the signal at the microphone. And you can add sources to create an acoustic scene. And this is obviously very powerful in audio simulation. So let me just say a few words. What's a room impulse response? Well, it represents the acoustics in the room. So, for example, it has a direct path representing the distance from the source to the microphone and the amplitude, obviously. And it has the first reflections from the walls of the room and the relative scale of direct and early. That is also saying something about what's the distance to walls and sources and all that. Early reflections will cause a coloration of the signal, whereas the late part of the room impulse response will give it sort of an echoic flavor, and that's determined by the absorption of the room largely. With that being said, so now we have a very important ingredient, the room impulse response. How do we get room impulse responses if we do not want to go measure? We want to simulate to have all the full flexibility. Well, obviously, a very important method is the image source method, which I also believe Tone will explain in more detail later. It's very simple, but also very powerful. There are some limitations, for example, that in its basic implementation, microphones and sources, if you will, they float in free air. You cannot sort of have objects in rooms in the basic version. Then we also have much more accurate, but also very much more time-consuming methods such as FEM and BEM, wave-based methods, ray acoustics, statistical, and we have all sorts of combinations of these ways of getting room impulse responses. With that being said about room impulse responses, we are sort of ready to build our first model here of the speakerphone voice pickup situation. We can put a noise source in a room and convolve it with its impulse response to the microphone. We can put a voice source in the room and convolve it with its impulse response to the microphone. And we can similarly, we can put an echo in the room and convolve by convolving the fine signal with a room impulse response. Having said that, we can formalize into a sort of a very first model of speakerphone voice pickup, where we combine databases of speech, noise, and sort of speech that's been played back by a loudspeaker, and through randomization and room impulse responses, we can add up into a microphone signal. A lot of details can be added here and designed in to really match reality. The sky's the limit. But this is sort of the basic picture of it. And it can very easily go wrong, so meaning that the quality of the trained AI process, maybe to remove echo, is not very good at the end. And that could, for example, be because we did not get the sound pressure level of the sources right for the application, or the room impulse responses were flawed in some way, the assumptions were wrong. It can be that we did not correctly represent the speaker, non-linearity, or many other things, similar to the accidental copyright tags in the image classification example. But if we are lucky to get it right, then I think we got it almost right in this sort of work in progress, where we did simulate data for the echo control problem explained previously, and we did train a DNN component in a hybrid DSP DNN system to remove echo. It does not do dereverberation, removing the echoes of the room in this example, but just the feedback echo from the loudspeaker. And let's listen to this example. So we have the input again, the French guy going to Paris that we want to remove. Let's listen to that one again. And when that's played a bit, I will play the output so that you can hear what the neural network learned removing the echo, and we can hear the underlying speakers. Let's listen to that.
That's good. You're going on
Thanks a lot.
vacation?
Thanks a lot. Yes, I would be very soon in vacation, and I'm
Okay.
really
So
looking forward for that.
Where are you going?
You know, I already told you that I'm going to France and in Paris.
And now the echo controlled signal.
That's good. You're going on vacation? Okay. So where are you going? Yeah.
But a
France.
specific city.
But there are many places in France, really. So it's
yeah. So we heard
Okay.
that it worked to some extent. If time allows, and I think it does, I can just mention a second application that we also did, and that is direction of arrival detection, where we want to find out where a user speaker is relative to the array, and that can be used for various purposes. For example, finding out who is talking in a meeting and so on. What we did was simulate audio coming from speakers from different angles, and then we trained a neural network to sort of output what angle is the current speaker coming from. And here's an example from a result from a room where we put 3 people in a room, and the red lines here are indicating across time where the ground truth of the speaker position, and the little green dots here are indicating who is speaking or indicating where sound is coming from. And we see that the green dots nicely coincide with ground truth, meaning that it works to some extent. So quickly concluding here, you can go wrong in many ways, but it's also a very powerful tool to simulate your data for audio processes using AI. And I think that concludes my talk today.
Thank you. We have a question here. It is, would you target to train a generic GNN model that is capable of enhancing the speech signal in a variety of scenarios? Signal to noise ratio, RT60, or rather a specific DNN model for each signal to noise ratio, and then perform model selection on the fly. I hope I read it correctly.
Yeah. Thanks for the question. It's a good question. I think it's a very large question in the sense that depending on application, in some applications, we could afford to train specialized models and apply them, for example, on the edge by switching between models. That could also happen in cloud. In other cases, maybe we are a little bit squeezed that we only want to have really one network that's generalized to the use cases that particular device could experience. So that would be a little bit depending on the case, I would say. And also, what was the benefit of the particular specialization? But we, of course, we have seen also a lot of work by others that if you specialize, then you can do better with under a parameter constraint, for example. So that would be my initial answer.
Thank you. Then we have another one. Which approach would you recommend to simulate the loudspeaker non-linearities?
That's also a very large question. I'm not sure we know the answer to that difficult question. Of course, we have some ideas of the electroacoustics here. So we have some models in mind from simple to complicated. I don't think I will sort of disclose our pet model here, but we know of sort of relatively simple non-linearities that are also described in the literature that work fairly well. But then again, here we also have to look at what particular device do we have in mind for this process. There may be something we know there that's best to put in the model of the transducer, the loudspeaker.
Yeah.
Some people have also sort of trained AIs to learn the non-linearities. That's also a way, but it's the one difficulty here is that it's a little bit difficult to sample a lot of devices. I mean, in deep learning, you typically want to learn from a lot of examples, and it's a little bit difficult to get your hands on a lot of examples of, say, device A.
Great. Okay.
I hope that helped.
Another question. Yeah. And otherwise, if you find that your questions are not answered, you can always return. Do you also simulate the directivity, it says, or maybe directionality of microphones, speech and diffuse background noise? I'd imagine that there would be a difference in coherence between microphone signals, both for speech and noise.
Yeah, so this is of course something we are looking at in different ways. That makes a difference when the microphones are either the microphones are directive or they become directive through the body in which they are embodied, so to speak. That can make a difference, and sometimes it can help, and sometimes maybe not so important. That's yeah.
And I think we have time maybe for another question. Recently, we saw an earbud with AI and trained with 500 million voice samples. How many voice samples are you going to claim with your simulation method?
Yeah, so typically the voice component, I think, is very often that we use, say publicly available voice databases. And we can get a long way with augmenting these before inserting them into our, let's say, scene creator or audio simulator. So on that note, maybe we don't need, or in that component, the speech component itself, maybe we don't need something extra. I'm not sure, but this is my answer. Yeah.
Great. Let me just see if we have a final one. What are the implementation challenges of DNN solutions on real-time operations and Jabra devices?
That's also a very large question, because it depends on the device. Some devices, they are running on very small batteries. Some devices sort of in the milliwatts. Some devices are running in the watts almost. And some devices are running, and some processes are running not on the device, but somewhere else. So it depends on that, what kind of a vehicle you have available for your DNN, say. But if it's in the case where miniaturization is required, then of course you have to pay a lot of details to the techniques involved in miniaturizing neural networks. That could be quantization, optimizing the model structure, and so on. Also, one constraint, for example, is for many audio processes, you want to be more or less causal. You cannot analyze use signal from the future to analyze it. We need, as we speak here in this call, my speech needs to reach your ears sort of at real time. That's one constraint. So those are sort of the available computation resources is one thing, and causality is another one. I don't know, could I come up with more on the fly here? Yeah, of course, the performance needs to be really good. That's number one, maybe. For all our use cases, the point I try to stress that users do strange things with the device. That's good, but and we try to anticipate that, and we learn all the time. But we need to get around making it work in all cases.
Yes, thank you, Rasmus. I think we have a few more questions in the chat, but I think we'll have to move on to Romain, and then we'll see if we have a bit of time at the end of the session to answer the remaining questions. Thank you, Rasmus, and please go ahead, Romain.
Okay. So thanks for the invitation first. Today I'm going to talk about sound event detection with synthetic soundscape. This is something that did happen during the Dks Challenge and the task for the Dks Challenge. So this is not work I did by myself, and all of these persons have been involved at one stage or another. Now the question is, first question is, what is ambient sound analysis and why would we want to do that? So basically here we are considering everything that is not speech or music. So for years, people have been focusing on dealing with speech, dealing with music, sometimes dealing with animal sound, but everything else was considered as noise and something we should throw away. Why would we want to analyze this sound then? Well, if you take a step back and think about this morning, then maybe first you had your alarm clock that rang and woke you up. Then you went to the kitchen and brewed some coffee, have the breakfast, discussed with family, and then went to work, for example, biking in traffic. And so if you think back about what happened there during your morning routine, then you've been relying on sound, and not only on speech, but on variety of sound all the way through your morning routine in order to know that the coffee is brewed, or in order to know that a car is passing by. And this is something we heavily rely on as humans. And this is something we want to be able to categorize with algorithm. And so the idea is first, being able to categorize the sound. So what type of sound am I listening to? And also to detect them. For example, if there is an alarm sound or something that is a car passing by or something, and I know that I should react, then I want to detect this kind of sounds. In our case, we are going to narrow down the ambient sound analysis to sound event detection task. And so here, the idea is I have a sound recording, and I want to know what happens during this recording, but not only what happens, but when did each event happen. Okay, the work I'm going to talk about here did occur during the Dks Challenge Series. So just a few words about that for those of you who don't know this challenge series. It's a challenge that started running in 2013 and it became yearly in 2016. There is usually between 3 and 6 tasks. And last year we had 6 tasks with 127 teams participating. And here we are more particularly concerned about the task 4. So we're running sound event detection in domestic environments. So we are focusing on what's happened inside a house and not what's happened outdoor. And this is something running since 2018. So what are we trying to do? So we focus on sound that are happening indoor. We are using a subset of audio sets. Audio set, for those who don't know, is this large sound data set, ambient sound data set that has been released 6 years ago by Google. There is like 2 million clips. And we are focusing only on 10 classes to make the problem a bit easier. Now, the first point we tried to address when we started this, and this is related to what Rasmus talked about, is, well, at test time, we want to have so-called strong labels. So I want to have the class, and I want to have like timestamps to explain when the event starts and when the event stops. These labels are hard to get. They are really costly to get. They are prone to error and bias in interpretation regarding the offset location and the onset location. So this is really tricky to get those strong labels. And as mentioned by Rasmus, that we need a lot of data to train a system. So what we proposed was, okay, we provide you weak labels. So I have a clip and I'm just saying, okay, there is pitch, dishes, and vacuum cleaner in there, but I'm not saying when. And you use this data to train your system that is going to provide not only the class, but also the timestamps. Okay, and so getting weak labels is cheaper than getting strong labels, so we can use them for training, but something that is even cheaper is using unlabeled data. I just need to crawl them onto the internet or record it. There is no annotation. The most costly part in there is the annotation. So having unlabeled data is fairly easy. So the idea here was, okay, we give you a small set of weakly labeled data, a large set of unlabeled data, and you should train a sound event detection system. I won't tell the full story, but just jumping to conclusion, why would we want to do that? So once again, it's really long to obtain a strong annotation. It's prone to errors. Did it work well? Well, the performance was pretty low at that time. We had only 10 classes, remember, and we had like F score around 20%. So this is something that is not usable in a system. And I remember when we discussed about the task at that point, someone working in a company went to discuss with us and say, okay, well, all this is nice, but I can't do anything with a system that is performing like this. And one problem here is that, unsurprisingly, systems are bad at segmenting in time. We don't provide any timing information on the training, and we just hope that the system are going to learn this. And so this didn't work so well. So the proposal we had the year after was to exploit synthetic data. So here we are not going to position sources in a room and having those sources playing together, but we are going to position sources in time within a clip. And so the idea is that I have a set of isolated sound events from my 10 classes, and I have a set of background, so that are going to be texture sound, hopefully without any event of interest in there. And so I'm taking, for example, this running water, I'm putting it in a kitchen, and then I get my clip of running water in the kitchen. So this is a cheap way to get strongly annotated data. Granted that you design everything correctly in terms of time distribution, in terms of number of event distribution, you can get improvement of the system, and we quickly jumped from about 20% to 40% with this. But here in this talk, I'm not going to really talk about how did we use that for training, and do we want to have like non-target event in there? Do we want to have like really tight distributions or things like that? But something that we did realize when we did that is that we have a byproduct here, that we could use this synthetic soundscape to test systems. and to investigate whether systems are robust on specific conditions. So we are going to design soundscapes that are targeting one specific problem. So for example, we are going to vary the foreground to background signal to noise ratio. Or we are going to vary not the spatial localization, but the time localization of the sound event and see if the system reacts well to that or not. And the last one, which I won't present today, is we also try to simulate like sound degradation. So try to apply cell phone recording simulations or things like that. But let's focus on the first two. So the idea is that I have here my running water, I have my kitchen. And so if I'm putting a high gain on a running water, then I can see in the output clip that this is really salient. And it's going to be pretty easy to detect. Now I want to test what's happening if I go further away from the running water. And so I'm going to apply a smaller gain here and a larger gain on the texture. And then my running water is going to be more difficult to recognize here. So we did try this with random range considered. So going from more or less clean, because the lowest SNR was 6 dB to 30 dB, and going to cases where the event is at most as loud as the background. The second thing we want to consider is that as the system should provide the time localization of the event, we want to change to have the same clip, but with different time localization. So here I have still my water and my kitchen, but I'm positioning it at the beginning of the clip. And I could do exactly the same, putting it in the middle of the clip or at the end of the clip. And this is what we did here too. So we had 10-second clips, and we tried to put each time the same event at around 0.5 seconds, because if we put it exactly at 0.5 seconds, then the systems are going to learn that this is exactly 0.5 seconds, but somewhere randomly in there, somewhere randomly towards the middle or towards the end. Okay, now let's see what we could conclude from this. Here we are looking at event-based F1 scores. So this means that we are trying to map the event within a tolerance collar. So on the onset, it's a 200 millisecond collar. If you are within these boundaries, then the event is considered as a true positive. And for the offset, it's the maximum of 200 milliseconds and 20% of the event length. And we average everything over all classes. So the first thing, what we did is every people participating to the challenge was submitting the output of their system on these specific data sets. And so we can see that unsurprisingly, the performance is dropping when the SNR is dropping as well, which is not really surprising, but something that was interesting for us is that if we compare the performance we have here at 15 dB SNR, then we have performance for almost all of the system that is matching the performance we obtain on the real recordings. So this means that we are somehow getting close to the real recording condition. Second thing that we did investigate here is with our data sets. So here on the blue one, we are going to try to see if we can detect the onset of an event, of long event, if it's at the beginning of the clip, and the offset of an event that starts at the beginning of the clip. Then for the second one here, it's the offset and onset and offset towards the middle of the clip. And for the last one is the onset and the offset toward the end of the clip. So what we can see is that if my offset is reasonably toward the beginning or towards the middle of the clip, for long event, all the systems are going to work reasonably well. Now, if we look at what happens when my event is towards the end of the clip, then all the systems' performance collapse. And this is, at first we thought that, okay, this might be a bias we have in our training set. And we looked at the training set, but the distribution is more or less uniform over time for all the events. So this is not a matter of the training distribution. And we looked a bit more into detail. And here we have like some post-processing that are particularly non-causal. As Rasmus mentioned, sometimes we need some strict causality constraint. Here they have like long post-processing filter that needs to know at least a few seconds what is going to happen in a few seconds in order to decide whether an event is active or not. And so if your event is going towards the end of the clip, then it means that you don't have this look ahead and you're not able to recognize to detect the event. Whereas what we had in the baseline was rather simplistic. And so we're underperforming compared to those other systems, but at least we're able to perform also with a small look ahead. And so here we are talking like about 500 millisecond look ahead, which is rather long if we consider like speech processing for human-to-human interaction. We are not going to look at 500 millisecond delay. Okay, and so this is the end of my story for today. And if there are a few takeaway points, is that there is something that we did try to investigate, and that is really important, and that Rasmus mentioned as well. And it's we have to make sure that we don't have so much domain mismatch between the synthetic and the recorded clips. Otherwise, the system is not going to work on our test data. And for this, we did try to take the audio set data set and compute the event distribution per clip or the event co-occurrence in order to make sure that I don't have a vacuum cleaner and a car passing by in the same scene. That's something you want to keep things realistic. The second thing is that you are going to compute all these aspects on a data set pre-existing or on a set of constraints you are going to fix. And so you might have some biases here. So in our case, we are using audio set. There is biases in terms of event distribution. There are a lot of events happening because it's people recording with a smartphone. So usually when I film something and put it on YouTube, is that something is happening. If I put a device in a home, then most of the time nothing is happening. So I have like way too many events in audio set. And also the recording condition, am I getting close to the sound events or not? And usually when I'm filming something to put it online, then I'm getting close to the action, which is not going to happen if I have a device posted somewhere. And then the second idea here, and that's something we've been working quite a lot on these past years, is try to use the synthetic soundscape to isolate the scientific challenge as much as possible in order to have a diagnostic of what's working or not on a specific point for which system. And now what we want to do next? So it's nice to simulate data. That was a nice jump, but is it still going to be the case with the use of external data? If I use like those large data sets, if I use model pre-trained on ImageNet as people have been doing, do I still benefit from the kind of knowledge and expertise I've been putting in crafting my simulated soundscape? And that's something we are trying to investigate. And we also want here, but which is not directly related, but as a more opening, is to monitor the power consumption of this system. And because I could generate like billions of clips, but is it at some point, is it still efficient? And at some point, do I just start like burning energy, but not winning anything in performance? And also a problem we have here is what do we want to do with the metric? And currently I've been talking about only simple number, but that's something we probably like want to go beyond at this stage. And just a shameless plug to conclude here. As I've been talking about the Dks Challenge, we are organizing here in Nancy in November, Dks Workshop 2022, and there is a submission deadline in a month. So get in touch if you're interested. And I'm ready to take your questions.
Thank you, Romain. We do have a question here. Did you consider acoustic augmentation, e.g. trying to modify room microphone characteristics?
We did at some point, because at some point we were trying to investigate, as we saw that the background to foreground ratio is degrading the performance. We did investigate having like sound separation. And so as the next step in the sound separation here is single channel, but the next step was multi-channel. And so we did try to have specialized sound scene. So instead of just mixing everything and applying like what Skipper does is just applying the source reverb in order to blend a bit the event in. What we did is select few events, select simulated room impulse response in the room, and put all the events there and try to simulate this. And we try to also simulate different room with different reverberation time and so on. And unfortunately, and we were a bit disappointed, but trying this at training did not improve. It was degrading the performance. And we tried to understand what was going on. We didn't get really to the bottom of it, but we were all surprised and a bit disappointed. One of our assumptions is that there is already all these isolated examples we have, they come from free sound. So they could already integrate some a bit of reverberation, plus the background recording are also recording from a distance, and so adding like some reverb on top of it might be leading to some destructive effect. The second aspect is that maybe we were not on the same or similar condition as the one we are experiencing in audio set. So maybe we had too much reverb or not enough, or but
Yes, thank you. Another question is, how can sound event detection be performed on a stream of audio data in which no relevant events occur most of the time, rather than on short audio clips?
So that's something we tried, and that's what I say like about audio set. If you take a 10-second clip in audio set, you usually have we have an average of 3 to 5 events occurring in 10 seconds. If you record yourself at home or something, you'll see that this ratio is dropping quite a lot. And we did experiment like recording like 1 hour of daily life or something. And so we did try to using the synthetic soundscape, we did try to have longer clips, but without the same event distribution. So with much lower event distribution. So I would have 5 minutes and I would have like 4 or 5 events occurring within 5 minutes. And the answer is some of the systems are really overfitting the training data distribution and are really biased toward what's happening in audio set. So this means that they are outputting event quite a lot. And if you try to do that on this long clip, then you'll have a lot of false alarm. And some approaches were a bit more robust to that. And then in order to go a bit beyond that, we did try to also provide recordings where nothing is happening, or recordings when things are happening, but they are not event of interest. And most of the systems still do recognize something. So this means that if we are training on this audio set data, then we are incorporating the bias of audio set within the models. And at test time, if we are not in these conditions, then we are going to have problems.
Yes, we have another question. Is this a single microphone processing, or can it be applied to microphone array recordings as well?
So this one is a single microphone processing. We have colleagues who are working on multi-channel processing. But what they do when they do multi-channel processing is that they try to localize the event in time and in space. But there is only really little work about, I have multi-channel processing and I'm trying to use the spatial data to separate the events. And I mean, saying, okay, I have 4 or 5 microphones, I don't care where the sound is coming from, but I know that I can have like 3, 4, 5 concurrent sound, and I know that they are not coming from the same space, and so I want to apply multi-channel processing to split the stream into different separated streams.
Thank you. I think that's it for the questions for this session. No, there's another one. Can you elaborate about audio characteristics? Any required pre-processing?
I'm not sure. So we don't apply any pre-processing at this stage. It's just, we just have a standard feature extraction. We use, most of the people use log-mail spectrogram. We did try at some point to use single channel sound separation. And single channel sound separation that was working pretty well, because when we were listening to this, we had like separated events and they were sounding pretty good. Looking at the metrics like a signal to distortion ratio and things like that, they were pretty good. But then the sound event detection didn't benefit so much from that. And so it was putting heavy machinery before the sound event detection to win like 1 or 2 points in F1 score. And we were a bit also disappointed about that, but maybe as we are presenting clips with several overlapping events, then the sound event detection is probably implicitly learning to separate the stream at some point also. And giving the explicit pre-processing didn't change much.
Thank you. So that's it for the questions. Thank you very much for the presentation and answering questions, Romain. We actually do have another one here, but I think we'll save that for the end then and move on to Zoom.
Okay, thanks a lot. Let me share my screen. Okay, I hope you can see my screen all right. So this talk will be a bit more about acoustics, perhaps a bit of physics, slightly less about AI, but still I hope you'll understand the relevance for AI after this talk. So I will talk about simulation of room acoustics and reverberant sounds. And already Rasmus and also Romain briefly touched upon this and about the relevance for various audio AI applications. So what is room acoustics and what is reverberant sound? I think we all know that if sound is being generated in open space, then it sounds very differently than when it is generated in a closed environment, like a room or a hall or a church. And so basically room acoustics is the term that we use to refer to the combination of various propagation and scattering phenomena. So as you can see in the animation, when a sound source is generated inside a room, then sound waves will hit the boundaries of the room and will be scattered in various directions. And so eventually what you observe, if you would put a microphone in this room, for example, what you would observe is a superposition of the original sound wave, but also all these scattered sound waves with a certain delay and with a certain attenuation. And so this is what we would call the reverberant sound. If we put a microphone somewhere in this room, what we measure is not the dry original sound, but rather the reverberant sound, including the effect of room acoustics. And this is indeed relevant in the context of AI, not only for signal enhancement, where I refer to the talk of Rasmus, the first talk today. Indeed, if you want to do noise reduction, source separation, dereverberation, echo, feedback cancellation, etc., especially if you use AI-driven algorithms, then typically you need a data set to train and to test the algorithms. And of course, that data set should be as realistic as possible, which means it should include the effect of room acoustics. Next to signal enhancement, there's a number of other applications in the realm of audio acquisition that require simulated data, or that would benefit from having simulated data. I think the most typical example is automatic speech recognition, which is perhaps one of the oldest examples on the slide here, where in the early days, people would use dry speech recordings to train ASR engines, but nowadays it's very common to use reverberant speech data. Same thing goes for event detection, which is what Romain was talking about. But sometimes we're also interested in solving room inference problems, like localizing sources, localizing microphones, estimating properties of the room, like the geometry. And then finally, there's a number of audio reproduction applications that are nowadays also AI-driven, like synthesizing virtual acoustic scenarios, for example, for gaming or virtual reality applications, and spatial audio. And of course, these real-life reverberant data could be acquired by means of measurements. And as Rasmus already mentioned, not only would this be very time-consuming, but also it becomes very tedious then to have a ground truth with those data measurements, to have data labels. And in fact, data simulation gives us a very attractive alternative, not only to generate massive amounts of data, but also data that come with labels. For example, if you generate reverberant speech data and you have labels in terms of phonemes from a dry speech data set, then you can use data simulation of room acoustics to generate a reverberant speech set, which still has the same labels as the dry one. Or, for example, if you want to generate, or if you want to solve source localization problems, you can easily simulate signals where you know what the correct location of the source is. And that's more difficult if you would start from data measurements. Now, this presentation will be based on a systems view of room acoustics. What do I mean by that? So we will consider room acoustics as a system where something goes in, so that would be the dry sound of the sound source, and something comes out, and that would be the reverberant sound. And this systems view on room acoustics can be considered in different frameworks. The most general framework would be a space-time framework where the input, so the sound source, is considered to be a function of space and time. For example, like here we have a two-dimensional spatial domain, and suppose there's a point source in the middle here. That point source can generate a time-varying amplitude, so that would be a function of two-dimensional space and time. And then the output would be a reverberant sound field, which again would be a function of space and time. So in this context, signals would be multivariable functions. This is not what we will do in this talk, even though it's a very interesting approach. We will restrict ourselves to a time-only representation. So that means we consider that we have a sound source that behaves as a point source, and we also have a microphone or an observer that behaves as a point in space. And we're going to model room acoustics from a point-to-point perspective. And then we can choose either we model things in continuous time, so then the input and the output would be continuous time functions, but of course it's more common to work in discrete time. And in that case, after sampling, we obtain vectors as an input and an output. In my notation, I will often use continuous time, but of course we assume that when processing signals, we actually work in discrete time. Now, in this system's point of view on room acoustics, what we want to do then is to, first of all, choose a model for room acoustics and then find a simulation method to simulate the parameters of that model. Now, there's a wide variety of models that we can use for room acoustics. There's a figure here that shows the different categories of models that we could use. I will not go into the details here, but if you're interested, you can find more on this in the slides of a tutorial that we gave a few years ago at UCIPCO. And in fact, the focus of today will be on these models here, convolutional models or FIR models. But one thing that is important to mention, and already Rasmus mentioned this in his talk, is that pretty much all of these models exploit two properties that hold, or that approximately hold, for room acoustics. First of all, room acoustics is a linear process. So the scattering and the propagation that I was talking about earlier are signal independent, and that makes this process indeed linear. Secondly, it is often assumed to be a time invariant process. And so that means we can restrict ourselves to the question how to model a linear time invariant system. And there's one fundamental result there that we will be using. If you provide a delta function at the input of a linear time invariant system, then at the output, you obtain a signal that is known as the impulse response, or in this case, the room impulse response. And for a linear time invariant system, these room impulse responses provide a complete description of the system. Again, as long as we assume a certain point source at one position and a point observer at another position. And more conveniently, in fact, we can compute the output to an arbitrary input of such a system by means of convolution. So if we compute the convolution of this impulse response that we will denote by h of t with an arbitrary input signal x of t, then we find the output of that particular room system. And of course, we can do this in a discrete time manner using the well-known method of discrete time convolution that is displayed in this animation. Let me then, well, before going into the first method that I want to introduce here, what is really the core issue here is the simulation of the room impulse responses. That's going to be the hard part of the task. Once we have the room impulse response, we know that the reverberant sound, so the output signal, can be computed by means of convolution. So conceptually, that is very straightforward. Computationally, that's another thing because it could be very computationally demanding. And so in terms of room impulse response simulation, the first method that I want to briefly discuss is a very well-known one. Also, Rasmus already mentioned it in his talk, that is the image source method. In fact, the image source method is an approximation, so it's a geometric approximation for what happens when sound scatters off a wall. And what we're doing here is we're not considering sound as waves, but rather as rays. So we can actually draw lines to indicate how sound is propagating. So if we have a sound source and we have a microphone, and suppose we have a single wall, then from a geometric perspective, we could say the scattering of this sound source signal of that wall can be represented by a specular reflection. Now, in the image method, this reflection of this wall is going to be modeled by a so-called image source. That is, we will pretend as if the wall is not there, and instead we replace the wall by a second source called an image source that is positioned here. And in fact, this is the projection of the original source position onto the wall, and those two distances, so the distance from the source to the wall and from the wall to the image source, are equal. And then, in fact, what the microphone observes is simply a superposition of the original source and the image source signal. So the image source completely represents the effect of the wall. Now, if we then know those two distances, so the distance from the source to the microphone and from the image source to the microphone, then we have everything that we need to simulate a simple impulse response. In this case, the impulse response of a single wall. And so we see there are two components in this impulse response. There's a direct sound and reflected sound, and both are modeled by means of a scaled and delayed delta function. So if the source emits a delta function, then what we will see is, first of all, the direct sound will be a delayed delta function according to the distance between the source and the microphone, and it is scaled due to spherical spreading. And the reflected sound component, again with a certain delay now depending on this distance here, and again spherical spreading that gives an attenuation, and also possibly some attenuation due to the wall. So this beta parameter here gives us the attenuation that is due to the properties of the wall. Now, of course, usually a room has more than one wall, and what happens if we have multiple walls, for example, two walls, then we will have to take into account higher order reflections, because basically these image sources get again reflected themselves. And so instead of only having first order image sources, as in the previous case, we also get second order, third order image sources, and so on. And if we then consider a room with 4 or actually 6 walls, if we're considering a 3-dimensional case, so now our room is displayed here. So this rectangle here, that's our room, and the Z-axis is coming out of the screen. Again, we have a source, we have a microphone. Now we need first order, second order, third order, and so on, image sources in each of the 3 dimensions. And eventually this leads to a simulation of the room impulse response as a summation of all scaled and delayed delta functions. Very similar to the case of a single wall, but now each of the walls creates not only a single reflection, but also these higher order reflections due to multiple reflections of different walls. What we need in order to be able to simulate this is all the distances DRL from the image source of order R with an index L that relates to which of the walls of the 6 walls we are considering here. And so the delays will be different for each of the image sources. Again, there's going to be a spherical spreading and the attenuation due to the walls. In a very simple case, if we assume all the walls have the same attenuation factor, is equal to beta to the power R, where R is the order of the higher order reflections. This may seem like a complicated way to simulate room acoustics, but in fact, if we are dealing with shoebox rooms, that is rectangular rooms, then these image sources form a regular lattice, and it has been shown that fast simulation is feasible in that case. And that's in fact why the image source method has become so popular. And there exists several open source implementations. A very widely used one is the MATLAB implementation by Emmanuel Habetz. There's also an implementation by our team that is particularly focused on a specific artifact known as a sweeping echo that can occur for shoebox rooms. And there's a very popular, fairly recent Python toolbox known as PyRoom Acoustics, in which many of the properties of the other simulators have been combined. Now, what are the strengths and weaknesses here? As I mentioned, the image method is very fast for shoebox rooms. It's conceptually simple, and it allows for massive data simulation, but only for virtual rooms. What are the weaknesses? For non-shoebox rooms, it is really not fast. It's computationally very demanding. It doesn't give us a way to simulate acoustics of a real room. And when we want to use the image method, we need detailed room information like room geometry, source position, absorption coefficients, etc. So then finally, I would like to introduce a second approach to simulate room impulse response known as the equivalent source method. If you talk to a mathematician, then they would rather call it the method of fundamental solutions. What does this method do? It approximates a sound field as a linear superposition of spherical waves emitted by a set of point sources that are not really there. And we call these equivalent or sometimes secondary point sources. And in fact, the image method that I just presented can be interpreted as a special case of this equivalent source method. In fact, in the animation down here, you see the image method, but now not using rays to represent the propagation of sound, but using spherical waves. And we see that indeed, according to this interpretation, we can interpret the sound field inside the room, which is a small box here, as a superposition of spherical waves originating from all these image sources in this irregular lattice. So the image method is one way to implement this equivalent source method. However, there are other ways as well. And one particular setup that I want to illustrate here is shown in the graph here. So again, we have a room. We see the top view of the room here. We have a source indicated by the point with the S here. And then we have a set of points here indicated by these labels W, and these are our equivalent sources. And what we want to do now is to simulate the room impulse response from this source to any point in this volume of interest here, denoted by omega, representing that room impulse response as a superposition of signals coming from these equivalent source positions. How can we do that? Well, in this case, and that's a major difference with the image source method, we are not assuming that these equivalent sources are delayed and scaled delta functions. No, they can be signals that we denote as WL that are different from delta function. So each of these W points can really emit a signal that is longer than just a delta function. And the superposition of all these signals inside this volume here is aimed to simulate the actual room impulse response of this room. So this leads to the following model where again you see a summation like in the image method, but now it's not a summation of scaled and delayed delta functions, but it's delta functions that are being convolved with each of these equivalent source signals, WL. Now the question then is, of course, how can we find these equivalent source signals? For this, we will perform so-called pressure matching. That is, we will put a number of microphones into an existing room, and these microphones, that's in fact the inner circle of dots that you see here. So these microphones, in this case 18 microphones in this figure, give us some pressure signals. And what we then do is we match these recorded pressure signals to the model of the room impulse response that we use, and the signals of the equivalent sources, these WL signals, act as unknowns. Now, in general, applying a pressure matching approach here will lead to a highly underdetermined problem. Why is that? Because typically we have many more equivalent sources than we have microphones. How can we solve this? Well, if we put everything into a neat matrix framework, we can formulate a minimization problem where we do not only perform pressure matching, that is the first term here, so we match the measured pressure with the delay and attenuation operator applied to these weight signals W, but we also impose regularization. And the regularization that we choose here is imposing so-called spatial temporal sparsity. So we want these equivalent source signals to be sparse in space and time. And that actually makes sense from a room acoustics perspective. Why that is the case, I will not go into details here. I want to finish with a short simulation example to show you the effect of this sparse regularization. So what you see here is a directional visualization of a room impulse response. So as the visualization moves forward, we move forward in time, and you see also the color bar here indicates time. So we start with a light color at time 0, and as we move forward, we move to a darker and darker color. And you see the so-called directional impulse response. So you do not only see when there is an amplitude arriving at the observer, but you also see from which direction, both azimuth and elevation, it is arriving. Now, this underdetermined problem of finding these equivalent source signals, if we solve it using let's say a vanilla regularization, which is Tikhonov regularization, or if we solve it with a sparse regularization, leads to a completely different solution. In the left case, you see that the solution is completely not sparse, which means there is energy coming from all possible directions. Whereas in the right case, you see that at specific time instance, there's only a few of these equivalent sources that are being active. So we impose indeed sparsity in time and space. What is not shown here, but you can find the detailed results in the paper reference below, is that the right model here, in fact, provides a better approximation of the true impulse response than the model on the left. So imposing this sparsity does indeed make sense. If you're interested in using this, there are also toolboxes that allow you to implement this. And just to summarize the main pros and cons of this approach, so this equivalent source method allows us to simulate a massive amount of data for real rooms rather than virtual rooms. We don't need any prior information about the room, such as geometry or the absorption behavior of the walls. And we can achieve a fast simulation of room impulse responses after we have found these equivalent source signals. The main drawback is that finding these signals is indeed a costly operation. So solving this sparsity regularized optimization problem that I showed is quite costly, but you only have to do it once, and then you can use those signals to simulate a large amount of impulse responses, but only in a small volume inside a given room. So that's the end of this talk. I'll be happy to take any questions.
Thank you. Yeah, we have one question here. Let me just see. How do the various room impulse function simulation methods compare computationally? Yeah, that's it. ISM, spherical wave, or TSM?
It really depends what type of room you're dealing with. So for shoebox rooms, ISM is absolutely preferable from a computational point of view because it can be implemented really fast. In fact, something I didn't mention here is that a further speed up in shoebox rooms can be achieved in the spatial frequency domain, where this regularity of this lattice of image sources can be further exploited. That is work by Richard Heusens from Delft University of Technology. But as soon as you go to a non-shoebox room, then the ISM becomes computationally problematic. And then certainly the equivalent source method becomes a very viable alternative, because you can basically do most of the computations beforehand, computing these equivalent source signals. And once you have these, you can simulate room impulse responses in a very fast way by just delaying and scaling these equivalent source signals.
Yes, thank you. Then we have another one. How is the simulated RIR evaluated?
Yeah, here what we did in the papers that I referenced is we compared the simulated RIR with ground truths, which is either simulated using another method, for example, a finite difference method, or which has been measured in a real environment. And of course, a further evaluation that you could do, but that's something we haven't gone into, at least not in this work, is to do a perceptual comparison of the reverberant sound. So if you would use these simulated impulse responses as together with convolution to simulate a reverberant sound signal, you could perceptually compare that to a real signal that is measured in the environment that you're trying to simulate. So that would be a perceptual comparison, but what we did here is really a comparison based on distances between impulse responses.
Thank you. Then we have another one. Equivalent source position and numbers are parameters, right? How do you select the equivalent sources, position and number? What is the impact on the RIR estimation and on the computation load?
Yeah, that's actually something we haven't gone into in detail. So what we did is we put all the equivalent sources on a sphere, which is at quite a distance from the volume of interest where we want to simulate the impulse responses. We have gone, I think, for there's like a way to distribute point sources on a sphere using a so-called Fibonacci lattice. That's what we use here. But whether or not that is optimal, that's a question we haven't looked into yet. The number of equivalent sources to use, clearly, if you increase that number, also the accuracy of the room impulse response simulation will increase, but it will come at the cost of a higher computational complexity. Again, it's mainly the complexity of computing these equivalent source signals that is the key complexity. Once you have these, simulating the room impulse responses is fairly computationally straightforward.
Yes, another question for you. Are the output room impulse functions of ISM and TESM methods identical, or can TESM be set to approximate ISM? If yes, how good is the approximation?
Yes, well, the equivalence between the two methods holds if we perfectly know the room geometry and if the room boundaries are perfectly rigid. And in fact, in those two cases, under those two assumptions, both methods provide the solution to the so-called acoustic wave equation. However, as soon as the walls of the room are not rigid, then both methods provide an approximation to the real impulse response or the real solution to the acoustic wave equation.
Yes, and we have another one. You've focused on domain-specific solutions in AI context, whereas Rasmus and Romain mentioned general DNNs. Did any of you try physically informed or physically based deep learning models in your problem domains? I think that's more like a general question, maybe. But
Maybe I can go first. The simple answer for me is no. We didn't do that, but I think there's a strong potential there because we know a lot about the physics of room acoustics. At the same time, we see that using data is extremely powerful. For example, this equivalent source method is also a hybrid method where we partly use physical insight. So this sparsity constraint that we introduce is really a physically based constraint. But at the same time, we start from real measurements, which makes the simulated RIRs much more realistic than the ones obtained with the image source method. But we haven't gone to the step of looking at physics-based deep learning models yet.
so how about the rest of you, now that we are at this question, Rasmus and Romain, do you have any comments for this one?
I would say the same on my end. No, that was not the first thing we tried to incorporate physics in the models directly, but that would more be on the data side.
Well, my answer is pretty close to Rasmus and Tom's answer. We didn't really try to include at least physics in the models. We did try to include like previous signal processing knowledge inside the model. What we've seen is that most of the time, if we try to incorporate it directly, then we end up with rather complicated systems and that are not performing much better. What do work pretty well, though, is just taking a signal processing based approach and replace like part of it with a smaller model. And so, but incorporating, in my experience at least, incorporating like DNN based models within, I'd say, old school signal processing is working. The other way around, trying to incorporate signal processing directly within a DNN based model, I haven't seen so many things working in that direction.
Okay, thank you. Another question for Toon. Are there any potential systematic artifacts that could be introduced using these simulation methods?
Yeah, absolutely. Yes. And in fact, one of the papers that I referenced on my slides refers to a specific artifact known as sweeping echoes that we discovered a few years ago. Well, we were not the people who discovered it, but we found out that, in fact, many existing simulation results in quite some audio literature, in fact, exhibit this artifact. And this is due to the fact that in the ISM, if you choose your room dimensions to be nice numbers, like integer numbers, and also your source and microphone position are integer numbers, then there's a very specific acoustic phenomenon that occurs, which is known as a sweeping echo. And it's actually not an artifact from the simulation method. It's something that really happens. You can, for example, hear it in nearly perfectly rectangular rooms like in squash courts, for example, but it's not something that happens in everyday rooms. And this was one reason why we introduced yet another ISM-based simulator that does a very quick fix to solve this problem, this artifact. Regarding the equivalent source method, one artifact that you could have there is that by imposing this sparsity regularization, you obtain an impulse response that hardly shows any diffuse behavior, which is very typical for the tail, the reverberant tail of an impulse response. So we keep on having quite discrete reflections even in the tail of the impulse response. That's the two main artifacts relating to the methods that I presented today.
Yes, thank you. Another one for you. Have you observed large performance differences when comparing data or augmented approaches to data simulated?
Yes, but it really depends how you use these simulated data. And in fact, that refers to one of the questions that was asked to Rasmus earlier today. Do you aim to train one generic model for reverberant sound, or do you aim to train specific models for specific rooms or rooms with particular acoustic properties, and then do a model selection depending which room you find yourself in? So we did some work a few years ago on reverberant speech recognition, where we looked at which room acoustic parameters correlate most strongly with ASR performance. For example, RT60 or direct reverberant ratio or clarity index. And it turned out that clarity index was the room acoustic parameter that correlated most strongly to ASR performance. So what we then proposed was a system where you could basically switch between different neural network-based models depending on the clarity index estimated in the room where you are present. And in that case, indeed, you see quite a significant performance improvement for ASR.
Yeah, then we have, I think, a last question for you. Does the RIR simulation method affect the data augmentation and the resulting performance of ASR sound event?
I think I just took that one already. Yeah.
Did we take that one? Wasn't it? I think there was.
Then I skipped the previous one.
Yeah.
About the noisy foreground.
Okay, sorry for that. I think they were just almost identical, actually.
Yeah, exactly.
They were two different people. Then there is one for Romain. How do noisy foreground events affect ultimate performance?
Well, if we consider the isolated events, we try to select them to be clean, or at least as clean as possible, because we know that we're going to combine them with other recordings, background sound, competing target event, and so on. And so we try to start from clean event in a similar way as when you do that sort of things with speech, you try to start with dry, clean speech. Otherwise, you're like accumulating things, and in the end, your simulated data doesn't mean anything.
Great, thank you. And we have another question for Rasmus. Is there any particular literature you would recommend for the topic you presented?
I would say no, really, not really. Maybe the hard truth is that to do this well, I think it's nice to go back to the basics and try and understand the machine learning, understand about training and testing and generalization and capacity of models or parameterized functions, and go back and learn about the DSP as well, and go back and learn about acoustics, and then maybe go to DNNs and learn about all the new stuff, new quotation mark stuff that's happening last 5-10 years. That's not an easy answer, or a nice easy recipe to, but that's best I can do. Sorry.
Great. Let me just see. I think one more came in. That's both Rasmus and everyone, I think. Which types of DNN architecture have you been using?
Yeah, so since I'm unmuted, I could start here. We've been looking at the usual suspects, I would say, and experimentally at a lot of things. So the usual suspects that are good in many cases, that's stuff like CNNs and variants of that, dilated CNNs, and then all the recurrent networks, variants, or some of them at least, such as LSTMs and GRUs and more.
Yeah, how about the rest of you?
So if, from my point of view, it's very application specific, and it depends on the mostly on the temporal properties of the signals that you're dealing with, like whether you only want to model short-term dependencies or also longer-term phenomena. So for example, for reverberant speech recognition, we've been using LSTM-based DNNs. We also did some work on speech emotion recognition, where the long-term context is even more important, like context of seconds or minutes or even hours. And then we used context stacked dilated convolutional neural networks. And then very recently, we also did some source localization work, where we used a so-called Siamese neural network, basically two neural networks operating next to each other. And then you look at the distance between the outputs and use that as a measure for distance in an actual metric space. So from my perspective, the type of structure you use is really dependent on the type of problem you want to solve.
Yes, thank you. Mark?
Yeah, my answer is going to be pretty much the same as Stone's answer. Like, it really depends on your application, and it also depends on the type of data you have at input also. Whether you are dealing with single channel, multi-channel, you are not going to deal with the same front-end processing, and the same goes with the way the type of annotation and the annotation granularity you have. If you have none, or if you have like super fine annotation, then it might also affect your network architecture on top of what Tom is mentioning. I would say that it might be, I don't know, disappointing for people, but at least here we are not using much of all the fancy latest stuff that have billions of parameters or something, but we are usually like dealing with much smaller network, and we are not going over 1 million parameters or something. And yeah, nothing too fancy, or try to keep those things simple in order to be like tractable. And I don't know, I don't have anything else to say.
Great. Yeah, we actually don't have any further questions from the participants, so I think we will just try to close the webinar here. Thank you, first of all, to our speakers. It has been a pleasure and very interesting topic indeed. It seems like our participants have been gaining a lot of knowledge from it as well, looking at the questions. And thank you also for participating. It means a lot to us in Danish Sound Cluster that we have the participants that support us with questions in the webinar, and also that we are able to provide you with knowledge. We've had a broad audience from the Danish sound companies today with us, so, and also we see some international participants, so that's really nice to see. Then I need to inform you once again that we have a questionnaire coming right up after the webinar ends, and that will mean a lot to us if you can answer that. It only takes a minute so that we can improve. We will send you the recordings and the presentations from the speakers, and then I have to remind you to watch out for our newsletter because we have a lot of interesting events and webinars coming up. So that's hopefully something from everyone. So that's it for us. Thank you very much, and have a nice day, the rest of the day at least. See you out there. Bye-bye.
Thanks, bye.
Thanks, bye.
Bye.